Tonight, we're going to look at something that feels easy to say, but is very hard to truly understand: the size of the universe. You've seen pictures of planets, stars, and galaxies many times before. Scientists talk about them often when explaining space. But here's what most people never stop to think about. When you really begin to understand how big the universe is, when you start to sense the scale it holds, it changes how you see everything around you. This is not just about large numbers or distant objects. It's about sizes so extreme that the human mind struggles to hold them all at once. From the smallest particles to the largest structures that exist, the gaps between them are almost impossible to imagine. And by the end of this journey, you'll understand why scientists need special ways to explain these distances, and why normal comparisons simply fail. Before we move on, if you enjoy slow, thoughtful explorations like this, a quick like or subscribe really helps the channel grow. It takes very little from you, but it helps this work continue. Now, let's begin. At the very edge of what we can measure, space itself seems to break down. The Planck length is smaller than anything we can see or touch, smaller than the gaps between atoms. It is the ultimate unit, the limit beyond which physics loses its meaning. Nothing we know can exist smaller than this. And yet, everything we call reality is built from structures far above this scale, but still far smaller than the world we move through every day. We begin with particles, the building blocks of matter. Electrons swirl around nuclei in clouds that define the edges of atoms, yet electrons themselves have no size we can measure in ordinary terms. Quarks hide inside protons and neutrons, confined by forces that are impossibly strong, shaping matter from within. Neutrinos pass through us constantly, billions every second without notice, invisible ghosts in the tiny universe within us. Their paths cross atoms, slip between particles, and leave no mark. The sheer number of these particles defies comprehension. A single grain of sand contains more atoms than there are stars in our galaxy, and each atom is mostly empty space. The nucleus, tiny and dense, sits in the center like a sun in a vast void, with electrons orbiting at distances hundreds of thousands of times greater than its diameter. Human minds cannot imagine such emptiness contained within solid objects. Molecules form from atoms, combining in patterns that build everything from water to DNA. Each molecule is a precise structure, held together by forces invisible to the eye, delicate yet unyielding. Life itself arises from these arrangements, yet the scale is so small it remains abstract to our senses. If you place a pinhead on a table, you can fit millions of atoms across its surface. A single drop of water holds countless molecules, each smaller than the smallest dot your eyes can see. At these scales, the rules of motion are strange. Particles behave like waves and like points at the same time. Light interacts with matter in ways that bend intuition. Probabilities replace certainty. Cause and effect blur into patterns that obey mathematics, yet defy everyday logic. Quantum uncertainty becomes a rule, not an exception. Energy flickers in discrete amounts, never smooth or continuous, and particles can vanish from one place and appear in another, leaving space between as if it had never existed. Time itself behaves differently here, as events measured in fractions of a second stretch beyond ordinary perception. Human senses offer no guidance. We walk through life imagining objects as solid, stable, and continuous, but atoms are mostly void. Electrons, bound by electric force, move in fields that we cannot see, but their influence is felt everywhere. Protons and neutrons, tightly bound by the strong force, form nuclei that are incredibly dense. Quarks inside them are held so tightly we cannot separate them, no matter the energy applied. The numbers become staggering. Consider a single cell in the human body, composed of trillions of atoms, each atom a miniature solar system of electrons orbiting a nucleus. Multiply this by the 40 trillion cells in an adult, and the total number of particles within a single human being is beyond ordinary counting. And yet, each particle is tiny, lighter than anything we can weigh directly. Pack them together, and they form objects, from dust to mountains, but always mostly empty space. Even space between particles is a stage for unseen activity. Virtual particles appear and vanish constantly, a background dance that gives rise to forces, shaping reality without notice. The vacuum itself is alive with fluctuation. Gravity, electromagnetism, the strong and weak forces, all emerge from interactions at this microscopic scale. Without them, atoms would not hold, molecules would not form, and life could not exist. Imagine a grain of rice. Divide it into pieces smaller than you can see, then again and again, until each piece is still larger than a nucleus. Place billions of those nuclei side by side, and you begin to approach the true scale of the atomic world. Even then, the smallest divisions remain hidden from direct sight. Quarks, electrons, neutrinos, these remain forever intangible, accessible only through experiments that infer their existence from effects on larger matter. Yet the patterns they form govern everything. Chemistry, biology, geology, and even planetary motion ultimately rely on these tiny foundations. Human intuition fails completely here. We are creatures built to perceive meters, kilometers, and miles, not nanometers, femtometers, or Planck lengths. Our brains cannot picture a trillionth of a millimeter, yet trillions of these units fit within the thickness of your fingernail. The smallest particles are not just small, they are beyond scale. Our concepts of size, distance, and mass are irrelevant. Numbers alone hint at magnitude. A pinhead holds roughly 10 million billion atoms. Each of those atoms is mostly empty, a lattice of protons, neutrons, and electrons, dancing in forces that shape chemistry and life. If you could shrink to the scale of quarks, the entire human body would vanish into a landscape of spinning fields and probabilities. Even the air you breathe is a forest of molecules, a dense jungle at microscopic scale. Particles collide, bond, separate, and move with energy patterns that determine heat, pressure, and light. Every sensation we feel is ultimately the sum of these tiny interactions. Your warmth, your touch, the taste of food, all emerge from the orchestrated motion of particles far smaller than you can see. And yet, these are the foundations of everything. Nothing larger exists without them. The solid world we experience is a mere illusion of continuity. Empty space dominates, and the minuscule defines. Quantum effects ripple upward, eventually shaping molecules, cells, and matter in forms we can see. These invisible processes govern the flow of energy, the reactions that create life, and the stability of stars and planets. They act everywhere, every second, unnoticed but essential. To imagine the universe at this scale is to confront the limits of human thought. The tiny is vast in number, and complexity arises from simplicity. One electron has no mass we can feel, but its presence maintains the structure of atoms. One neutrino passes unnoticed, yet billions stream through your body each second, carrying information from distant stars, remnants of explosions billions of years ago. Every particle tells a story, every bond, every interaction. And though invisible, these elements compose the reality we touch, the air we breathe, and the planet we inhabit. Understanding this scale requires humility. Numbers are abstract, but consequences are tangible. If a single subatomic particle were removed, matter might collapse, chemistry might fail, and life could not exist. The smallest components of the universe define the largest, and yet they remain hidden from view. They challenge perception, defy intuition, and demand observation through instruments that translate the invisible into images and data we can interpret. By the end of this journey, we will see how these minute scales connect directly to planets, stars, galaxies, and the full cosmos. What seems impossibly small is also the foundation for what is impossibly vast. And the question lingers: if all of reality begins with particles invisible to our eyes, how can we truly comprehend the universe that stretches beyond imagination? Life begins at the scale of cells. Each one is a tiny machine, a self-contained unit that breathes, moves, and reacts to its surroundings. Cells are smaller than anything we can see without a microscope, yet each one carries the instructions for life itself. Inside, DNA coils like a thread, folded with precision into shapes that determine what the cell can do, how it will grow, and how it will reproduce. Some cells float freely in water, some attach to surfaces, some work together to form tissues and organs. Bacteria are single cells, yet they are powerful. They can survive in heat, in cold, in acid, in radiation, in places where larger life cannot. Viruses are smaller still, not quite alive in the traditional sense, but they can hijack cells and use them to multiply. They move invisibly through air, water, and surfaces, shaping ecosystems without notice. A human body contains roughly 40 trillion cells, yet each one is invisible to our eyes. Each cell contains millions of molecules, a miniature world of constant motion. The scale is staggering. Imagine shrinking to the size of a cell. You would see a landscape of membranes, tiny organs called organelles, filaments that move materials around, and bubbles that transport nutrients. The nucleus would rise like a dense mountain at the center, the DNA inside twisting and turning, storing information far beyond human comprehension. Bacteria on a fingertip would seem like vast, bustling cities. Viruses would appear as hovering specks, each with the power to infect and change its host. Microscopes reveal a hidden universe of shapes and colors. Cells glow under certain stains. Some pulse with motion. Some divide, splitting into two, each carrying identical instructions. Others specialize, moving, secreting, defending. The variety is endless. Life's complexity begins at these tiny scales. Evolution operates here. Mutations in DNA may be minuscule. One letter changed among billions, yet the effects can ripple outward, affecting survival, reproduction, and species development. Every organism you see, from insects to humans, is built upon these molecular instructions, multiplied through countless generations. And the numbers are immense. In a single drop of water, there are millions of bacteria, countless viruses, and other microscopic organisms. The air is alive with cells and particles, invisible to our eyes. The soil teems with life unseen, roots of plants coated in microbial communities. Oceans are dense with microscopic plants and animals that form the foundation of the food chain. Without this hidden life, the world we perceive would not exist. Every breath carries bacteria from one place to another. Every movement stirs cells that have existed for millions of years. The smallest organisms shape ecosystems, and the ecosystems shape the planet. Compare this to human scale. A single human is a landscape to bacteria. A fingertip can host millions of these tiny life forms, each moving, reproducing, interacting in ways we cannot see. A teaspoon of soil contains more organisms than the number of humans who have ever lived. The universe of life at the cellular scale is dense, crowded, and complex. Observe cells under a microscope, and they resemble a city in motion. Filaments stretch like streets, vesicles move like vehicles, mitochondria pulse like power stations, keeping the city alive. Each part has a role, coordinated with thousands of other parts, obeying chemical rules, reacting to signals, adapting to changes. Viruses appear as strange geometric shapes, sometimes spherical, sometimes spiky. They drift silently, waiting for opportunities to interact. Bacteria can swim using flagella, cluster into biofilms, or change form when threatened. Life at this level is not static. It is a constant dance of molecules, energy, and information. We rely on these processes without knowing. Digestion, immune response, growth, thought itself, all emerge from cells acting together. Their scale seems impossibly small, yet their collective impact is enormous. Consider the ocean. Microscopic plankton provide oxygen that fills the atmosphere. Microbes in soil recycle nutrients, sustaining forests and fields. Viruses control populations of microorganisms, keeping ecosystems balanced. Even in humans, the microbiome, the collection of trillions of bacteria and other microorganisms, affects health, digestion, and immunity. Life is inseparable from the microscopic scale. Without it, nothing could function. Sensory images under the microscope bring this hidden world to life. Cells twitch, divide, and die. Membranes ripple, vacuoles swell and contract. Colors appear when stained, revealing structures otherwise invisible. Tiny hairs called cilia beat in rhythm. Mitochondria glow as they produce energy. Even the smallest amoeba moves with purpose, extending its shape to capture food. The visual impression is overwhelming. Complexity emerges from simplicity. A single strand of DNA is just a sequence of molecules, yet it encodes everything necessary to build an organism. Copying errors, small changes, create diversity. Over time, these changes produce new species, new adaptations, shaping the living world we see. From a human perspective, this scale is hard to grasp. We live meters apart, measure in kilometers, and navigate with senses tuned for large objects. Cells, molecules, and viruses operate on scales 1 billion times smaller than our everyday experience. Yet they define us. Every thought, every movement, every heartbeat is ultimately the result of processes at this microscopic level. Imagine shrinking down further. You could pass through skin, enter a cell, and float beside a nucleus. You would see DNA twisting like a ladder coiled inside a dense sphere. Mitochondria would pulse, releasing energy in bursts. Vesicles would transport proteins like delivery trucks. Bacteria on the surface would be giants, patrolling like soldiers. The activity never stops. It drives metabolism, replication, adaptation. Life is not just at the scale we see. It is everywhere, invisible, relentless. Numbers remain staggering. A human body contains roughly 40 trillion cells. Each cell contains roughly 10 billion atoms. Multiply this across all humans, all animals, all plants, and the planet itself becomes a dense web of microscopic actors, each performing its function. The scale of life at the cellular level is the first step in understanding the universe. From here, we move outward, from invisible to visible, from microscopic to planetary, linking the smallest building blocks to the structures we inhabit. Cells reveal how scale dictates function. Microscopic changes can affect macroscopic outcomes. The universe of life is nested, like Russian dolls, where each layer depends on the smaller ones inside. What seems simple and solid is actually composed of countless interconnected microscopic systems, all obeying the laws of chemistry and physics. Without observing at this scale, nothing about life could be understood. From cells to organs to organisms, the microscopic world orchestrates everything, shaping evolution, health, and the continuity of life itself. And yet, despite our dependence on these systems, most remain unseen, operating silently under our notice, invisible yet essential. The scale of life begins here, where the small governs the large and the hidden determines reality. From the microscopic world, we move outward to the scale we can perceive, humans and the planet we inhabit. Each human stands on a surface that feels solid, yet beneath our feet lies a layer of rock, soil and water that stretches deep into the Earth's interior. Cities rise like clusters of detail on a larger map. Streets, buildings and highways form networks that can be seen from the sky, yet they are small against the contours of continents. Mountains tower in height compared to humans, but even the tallest peaks, like Everest, are small when measured against the full curvature of the Earth. Oceans stretch farther than any human can walk. Their waves reach across thousands of kilometers, touching continents far apart. Rivers carve paths that seem long to our feet, yet they are tiny lines when measured across a continent. Each continent spans thousands of kilometers. Asia stretches over 8,000 kilometers from east to west. Africa covers nearly the same distance from north to south. The distances are enormous compared to human walking, yet minuscule compared to Earth's size in space. The planet itself is roughly 12,700 kilometers in diameter. Its volume is over 1 trillion cubic kilometers. The mass of the Earth is immense, yet we only notice a fraction of it through gravity, the invisible pull that keeps us grounded. Rotation shapes life in ways we feel but rarely see. Every day, the planet spins once around its axis, creating day and night. This motion is steady, yet the speed at the equator reaches over 1,000 kilometers per hour. We do not feel this movement, yet it is constant, an ever-present rhythm beneath our feet. The Earth orbits the Sun at nearly 30 kilometers per second, completing one circuit every year. This motion, combined with tilt, creates seasons. The angle of sunlight shifts, temperature changes, and life responds. Plants bloom, animals migrate, ice forms and melts. Life is tuned to the cycles of the planet, the rhythm of rotation and orbit. The Earth also wobbles slightly, a motion called precession, over thousands of years. This subtle shift changes the orientation of the axis, affecting climate patterns and the night sky. It is slow, nearly imperceptible to humans, yet it plays a role in long-term cycles. Humans, small and brief in lifespan, live entirely on the thin skin of the planet. Our cities, roads and farms cover only a fraction of the surface. The majority of Earth is untouched by direct human presence. Deserts stretch endlessly, forests rise with little interference, oceans cover most of the globe, and polar ice stretches to the poles. From orbit, continents appear as patches of color. Oceans dominate, reflecting light, while mountains cast shadows that hint at scale. No human could cross these distances in a single life, yet the planet supports billions of lives at once. Consider the contrast between a city and a continent. New York is home to millions, yet it fits within a tiny area compared to North America. A walk across a city may take hours, across a continent, months. Across the Earth, years or lifetimes would not suffice on foot. Oceans separate continents, thousands of kilometers of water between them. Ships take weeks to cross, planes hours. Yet even the fastest human technologies cannot move across the planet as quickly as the motions of the planet itself. Earth's rotation and orbit move the surface through space faster than we can travel across it. Even our tallest mountains and deepest oceans are small perturbations on a moving sphere. The oceans themselves carry currents that travel thousands of kilometers, distributing heat and nutrients. The atmosphere circulates winds and storms, moving energy around the globe. Human scale is dwarfed by these planetary systems. From the perspective of an ant or a human, the planet feels vast. Yet from space, Earth appears as a small sphere, a single object orbiting a star. Its diameter is 12,700 kilometers. Its circumference at the equator is about 40,000 kilometers. The surface is mostly water, roughly 70%, with land masses forming irregular shapes. Earth is layered inside. The crust is thin, as skin compared to the mantle and core. The mantle is solid, yet flows slowly over millions of years. The core contains iron and nickel, generating the magnetic field that shields life from radiation. Gravity emerges from this mass, pulling every particle toward the center. Rotation, mass, and orbit combine to shape every life process, every movement, and every climate pattern. Humans, aware or unaware, respond to these motions. Our sleep cycles follow day and night. Seasonal changes dictate agricultural patterns. Ocean tides caused by the moon's gravity affect marine life and human activity. Even small local shifts in gravity or geology influence life over generations. Distances are vast at this scale. From New York to Tokyo is nearly 11,000 kilometers. From the North Pole to the South Pole is over 20,000 kilometers. These measures seem immense, yet are tiny compared to the distances in space. Mountains, rivers, and deserts define regions, but their size is small when measured against Earth as a whole. The tallest mountains are less than 1% of the planet's radius. The deepest ocean trenches are even less. Cities cluster in fertile regions. Deserts and tundra remain sparsely populated. Life concentrates where energy, water, and resources are available, showing that scale affects survival and distribution. From above, humans are patterns on a moving sphere. Our roads, buildings, and farms are temporary markings on a surface that will change over millennia. Erosion reshapes mountains, rivers carve valleys, glaciers shift landscapes, and tectonic plates move continents. These motions occur over scales far beyond human perception, yet they govern the conditions for life. Earth is not static. It spins, wobbles, orbits, and shifts continuously. Each motion affects climate, weather, and ecosystems. A single year is a small increment in the planet's life, a brief moment compared to the slow drift of continents and ice sheets. Humans perceive stability, yet the planet is dynamic. Our cities seem permanent, yet geological time moves faster than human history in shaping mountains, oceans, and valleys. Distances define perception. Crossing a city takes hours. Crossing a continent, weeks. Crossing the oceans, months or years. Yet all of this is contained on a sphere 12,700 kilometers wide. Even this is small compared to the Sun, the nearest star, or the distances between stars. But at this scale, human life is contained entirely on one surface, limited to a thin layer of air, water, and soil. Understanding the Earth's size, shape, and motion is the first step in placing humanity within the wider universe. We measure in kilometers, we map continents, we navigate oceans, yet these scales are only the beginning. Beyond the planet lies the solar system, vast and complex, where distances stretch far beyond human experience. But even on Earth, scale governs life. Mountains channel rivers, oceans transport nutrients, and rotation drives winds and currents. Gravity, mass, and motion shape every process. Humans, for all their perception, remain small and brief on this moving sphere. Our cities, though large to us, are minor features on the surface. Our footprints last years, centuries at most, while the planet reshapes itself continuously. Understanding human scale in relation to the Earth is essential to understanding the next layer, the solar system, where distances and sizes expand beyond imagination. And if Earth itself feels vast beneath our feet, how can we measure it against the immense void surrounding it? Stepping beyond Earth, the scale grows rapidly. The moon rises in the sky, familiar and close, yet it is nearly 400,000 kilometers away. That distance is 10 times farther than the width of Earth itself. When we look at the moon, it appears near and small, yet space stretches between us, empty and vast. It takes light just over a second to travel from the moon to Earth. Space feels close in human terms, but even our nearest neighbor is far beyond immediate reach. Beyond the moon lies a collection of planets, each orbiting the Sun at its own distance. Mercury orbits closest, a small rocky world, just 58 million kilometers from the Sun. Venus follows, dense with clouds and heat, at more than 100 million kilometers. Earth, the third planet, travels around the Sun at 150 million kilometers. Mars, the red planet, follows at over 200 million kilometers. The gap between planets is immense. Even at the speed of the fastest spacecraft, it would take months to reach Mars. Jupiter is a giant, more than 5 times farther from the Sun than Earth, a sphere of gas many times the size of our planet. Its moons circle like miniature systems, each with their own landscapes and gravity. Saturn, Uranus, and Neptune follow, distant and cold, stretching billions of kilometers from the Sun. Their distances seem impossible, yet in the scale of the solar system, they are still part of one family, bound by gravity, orbiting the same star. Between Mars and Jupiter lies the asteroid belt, a thin band of rocky objects that varies in size from pebbles to dwarf planets. These fragments move quietly along their orbits, remnants of formation, a record of the early solar system. Space is mostly empty. Even between these objects, millions of kilometers pass without matter. The Sun dominates the system. Its diameter is over 1 million kilometers, more than 100 times the width of Earth. Its mass is nearly 300,000 times that of our planet. It supplies energy that drives life, shapes climates, and defines seasons. The light it emits travels across the solar system, reaching Earth in 8 minutes and 20 seconds. Mercury basks in sunlight in just 3 minutes, while Neptune waits over 4 hours for a single ray. The Sun's gravity holds planets in orbit, dictates speeds, and sets the boundaries of the solar system. Without it, these worlds would drift into space. Planets vary in size dramatically. Mercury is small and dense, a fraction of Earth's volume. Venus is close in size to Earth, yet shrouded in clouds and extreme pressure. Earth itself is the reference, a medium-sized planet supporting life with the right balance of distance and conditions. Mars is smaller, less dense, its surface red and cold. Jupiter dwarfs all rocky planets, a sphere of gas larger than all others combined, with storms that rage for centuries. Saturn's rings extend thousands of kilometers, delicate yet visible across the system. Uranus and Neptune are icy giants, distant and slow, their blue hues hiding complex atmospheres. Distances between these worlds are vast, stretching human intuition. Flying from Earth to Jupiter would take years at the speed of modern spacecraft. Even radio signals, traveling at the speed of light, take tens of minutes to reach the outer planets. Space, in human terms, is enormous. And yet, the solar system is only a tiny fraction of the galaxy. Light crosses the inner planets almost instantly, yet it takes 8 minutes to reach Earth from the Sun. This measure, light speed, becomes a natural scale. Distances shrink into seconds and minutes when measured this way, allowing comprehension of immense space. Moons orbiting planets show additional complexity. Earth has one, familiar and reflective. Jupiter has over 90, Saturn over 80, each a world in its own right. Some are icy, some rocky, some volcanic. Their presence adds layers of scale and motion, miniature systems within systems. The asteroid belt reminds us of formation and destruction. Thousands of objects, mostly small, drift in stable orbits, while occasional collisions produce fragments that journey inward or outward. Space is dynamic, even in seeming emptiness. Comets travel in elongated paths, icy bodies from the outer reaches, returning rarely after centuries. They remind us that the solar system is not static. Planets and smaller bodies interact, influenced by gravity and motion. Orbits are paths defined by mass and momentum, predictable yet vast. The Sun emits energy continuously, photons streaming outward, a constant flow across billions of kilometers. Solar wind carries particles that reach far beyond the planets, shaping magnetic fields and planetary atmospheres. The scale of this energy dwarfs human use. 1 second of sunlight hitting Earth delivers more power than humanity consumes in years. Comparisons between planets reveal contrasts. Rocky planets are small, dense, and relatively solid. Gas giants are vast, composed mainly of hydrogen and helium, with storms that could engulf Earth. Moons, rings, belts, and comets add complexity, revealing diversity across the system. Distances grow, even between neighbors. Mars to Jupiter is hundreds of millions of kilometers. The inner planets are crowded closer, yet the outer giants stretch vast gaps. Even light takes hours to traverse the far reaches. Spacecraft measure distances precisely, sending signals and returning data over months and years. The solar system is a family bound by the Sun's gravity, yet its members vary wildly in size, composition, and orbit. From Earth, it is hard to imagine the emptiness between objects. Yet all these worlds are connected, part of a dynamic system that formed over 4.5 billion years. The Sun anchors them. Its gravity, energy, and presence define the scale and pace of the system. Each planet moves at its own speed, following elliptical paths, interacting subtly with neighbors. Moons orbit, asteroids drift, and comets swing past in long arcs. Even within this small corner of space, complexity and scale are staggering. Distances are easier to comprehend with light as a measure. From Earth to Sun, 8 minutes. To Jupiter, 42 minutes. To Neptune, over 4 hours. Each number highlights how empty space dominates. Planets appear close in the night sky, yet vast voids separate them. The largest, Jupiter, is more than 1,000 Earths could fit inside, while Mercury is smaller than our Moon. Density and composition vary. Rocky planets are hard, gas giants soft in comparison, their atmospheres stretching thousands of kilometers. Rings add detail. Moons add layers. The system is a three-dimensional network, constantly moving, almost unimaginable in scale, yet observable from Earth. Even the speed of light, which seems fast to us, emphasizes emptiness. Signals take minutes to hours to cross the system, showing that human travel is slow compared to planetary motion. Understanding Earth's position in the solar system is essential before moving to the stars. The distances, sizes, and interactions in this system set the stage for the larger structures beyond. And as the solar system appears vast and complex, the question grows: what lies beyond, where distances are measured in light years and sizes dwarf even the largest planets? Beyond the solar system, the distances become unimaginable. Our nearest star, Proxima Centauri, lies more than 4 light-years away. Light travels at 300,000 kilometers per second. Yet even at that speed, it takes over 4 years to reach this tiny dot in the sky. To humans, 4 years seems long, but on a cosmic scale, it is a fraction of the distance to more distant stars. The solar system, which felt vast when measured in billions of kilometers, is minuscule compared to the space between stars. If Earth were the size of a marble, the nearest star would be several kilometers away. Stars are scattered across the galaxy, forming clusters, associations, and sometimes lonely travelers, moving through space with their own speed and direction. Our Sun is part of a family of hundreds of billions of stars in the Milky Way, a spiral galaxy with arms that curve gracefully outward from a dense central core. The core contains millions of stars packed tightly together, glowing with heat and light. Spiral arms, filled with gas, dust, and stars, wind across tens of thousands of light-years. Our solar system drifts along one of these arms, a small speck in a vast, rotating pattern. Stars move relative to one another. Some travel slowly, bound in clusters, while others race through space, perturbed by gravity and past interactions. Over millions of years, the positions of stars shift, constellations fade and reform, and new stars are born while old stars die. Nebulae, clouds of gas and dust, mark regions where stars emerge. Supernova remnants scatter material, seeding the galaxy, with the elements necessary for planets and life. The Milky Way is mostly empty space. Stars, bright and dense in appearance, are actually far apart. Distances are measured in light years because kilometers and miles are meaningless at this scale. Even the nearest stars are separated by trillions of kilometers. Between them, only vacuum exists, cold and dark. Yet this vacuum contains invisible particles, cosmic rays, and magnetic fields that thread through the galaxy. The solar system is a tiny island in this immense space. Its planets orbit the Sun, moving along in the galaxy at an average speed of over 200 kilometers per second. Over hundreds of millions of years, our system completes an orbit around the galactic center, passing through spiral arms near clouds of gas and dust, sometimes close to other stars. But even the closest encounters are distant in human terms, taking thousands or millions of years to traverse. The Sun moves in a nearly circular path around the core, tracing a slow curve through the galaxy, while other stars follow their own paths. The motion is smooth, yet the relative positions of stars change gradually. Gravity governs these paths, keeping systems intact and influencing neighboring stars. Star clusters form tight groups of stars, their mutual gravity holding them together. Some clusters survive for billions of years. Others disperse over time, spreading their stars across the galaxy. Within the spiral arms, new stars ignite, forming from clouds of hydrogen and helium. Young stars shine brightly, often with planets forming around them. Older stars drift along, moving away from their birth regions. Our Sun is a middle-aged star, stable, providing steady energy for life on Earth. Even within a neighborhood of nearby stars, distances are vast. Alpha Centauri, Barnard's star, Wolf 359, Lalande 2185, all lie within a few light years, yet each is a world of its own, hosting planets or potential planets, moving independently through space. The concept of scale becomes almost abstract. The solar system, with its planets and asteroid belts, is a single dot compared to the distance to the nearest stars. Light takes minutes to cross the solar system, years to reach neighboring stars. The emptiness between stars dominates space. Despite this, patterns emerge. The Milky Way rotates slowly, spiral arms winding around the dense core. Gas and dust clouds shape the birth of stars. Massive stars live short lives, exploding as supernovae, enriching surrounding regions with heavier elements. The galaxy is dynamic, but slow-moving in ways humans cannot perceive in a lifetime. We exist in a small arm, near the Orion Spur, a minor feature between larger arms. Our position is safe, far from the central chaos of the galactic core, distant from massive black holes and crowded clusters. Stars in the local neighborhood move at different speeds and directions. Some drift closer over thousands of years, others recede. Proper motion changes the night sky slowly, shifting the shapes of familiar constellations. Distances remain enormous. Even the closest stars are more than 4 light-years away. Voyager probes, humanity's furthest explorers, would take tens of thousands of years to reach them. Within this neighborhood, the scale of the solar system is tiny. The Sun, a medium-sized star, dominates its planets, but as we compare it to nearby stars, it is just one among many. Some stars are smaller, cooler and dim, others larger, hotter and brighter. White dwarfs, red dwarfs and giant stars form a spectrum of size and energy, yet all are separated by vast distances. Even within a few light years, the emptiness is overwhelming. Planets orbit stars unseen, tiny specks, yet these systems may harbor life or conditions similar to Earth. The motion of stars and systems demonstrates the dynamic nature of the galaxy. Stars interact gravitationally, passing close or slowly tugging on one another over millions of years. Some systems are bound, forming binary or multiple star arrangements. Others are solitary, drifting through interstellar space. Nebulae glow softly as light from nearby stars illuminates gas. Dust lanes obscure regions, hiding stars behind dark veils. These clouds mark both the beginnings and endings of stars. Supernovae leave remnants, scattering elements that later form new stars and planets. The Milky Way is a spiral, yet from within, its true shape is hard to perceive. We see only the patchy sky above, a plain of stars crossing the night. Deep space telescopes reveal structure, mapping arms, core and clusters. The local neighborhood is small compared to the galaxy, yet vast compared to the solar system. Each star could have its own planets, orbiting in silent motion, each world as small compared to its star as Earth is to the Sun. Distances dwarf human understanding. 4 light years, 10 light years, hundreds, thousands. Numbers lose meaning, yet they define the structure of space. Observing nearby stars shows movement over time. Proper motion, parallax, and rotation slowly change apparent positions. The galaxy is alive, slowly shifting, rotating, evolving. And as the solar system drifts along its path, we begin to see how tiny it is within this neighborhood, a speck in a grand celestial city, orbiting an ordinary star among billions. The question becomes clear. If even our local neighborhood of stars is so vast, what lies beyond, where distances stretch across hundreds of thousands of light years and structures dwarf entire solar systems? The Milky Way is immense, stretching across more than 100,000 light years. Its spiral arms curve gracefully outward, filled with stars, gas, and dust. The central bulge glows densely, a cluster of millions of stars packed tightly together. Gravity binds the galaxy, holding stars in orbit around the core, guiding the motion of planets, clusters, and interstellar gas. From Earth, the Milky Way appears as a band of light across the night sky. Yet what we see is only a fraction of its true size. Our eyes perceive hundreds of thousands of stars at most. Telescopes reveal billions, and the majority remain invisible without instruments. The galaxy contains over 200 billion stars. Some are small and dim, red dwarfs barely glowing. Others are massive, bright giants shining across hundreds of light years. Their light, traveling over millennia, reaches us gradually. Clouds of gas and dust stretch between them, shaping the formation of new stars while obscuring old ones. Spiral arms host star-forming regions, where nebulae glow softly, birthing young stars in clusters. Between arms lie voids, vast regions nearly empty of stars, silent expanses punctuated by faint light. Our solar system drifts quietly along one of the minor arms, a small speck against this immense backdrop. Gravity governs the motion of every star. Stars orbit the galactic center at hundreds of kilometers per second, taking hundreds of millions of years for a single circuit. Some move in clusters, tightly bound to one another. Others travel alone, drifting slowly through the galaxy. Star clusters, both open and globular, add structure and variation. Globular clusters contain hundreds of thousands of old stars, tightly packed in spherical formations. Open clusters are smaller, younger, and more spread out. Nebulae glow in soft colors as light excites atoms, forming new systems. Across the galaxy, dark dust lanes obscure parts of the spiral arms. The Milky Way's mass is enormous. Billions of stars, planets, gas clouds, and unseen dark matter contribute to the gravitational pull that shapes motion. The mass of the galaxy is roughly 1 trillion times that of the Sun. This gravitational framework defines the paths of stars, clusters, and interstellar gas. Compared to other galaxies, the Milky Way is average in size and mass. Some galaxies are dwarfs, tiny collections of stars spanning only a few thousand light years. Others are giants, hundreds of thousands, or even millions of light years across, containing trillions of stars. Elliptical galaxies appear smooth, lacking the spiral structure, while irregular galaxies twist chaotically, shaped by collisions and gravitational interactions. Clusters of galaxies form larger structures. Thousands of galaxies gather in groups and clusters, held together by gravity orbiting a common center. Between these clusters lie voids, vast empty spaces hundreds of millions of light years across. Filaments connect clusters like threads, creating a cosmic web. Galaxies move along these filaments, sometimes colliding, merging, or distorting each other. The scale is almost impossible to grasp. Human eyes cannot see individual galaxies at these distances. Even through telescopes, galaxies appear as faint smudges, their true size and complexity hidden. Each galaxy contains billions of stars, orbiting, forming new systems, and evolving over billions of years. The Milky Way itself will eventually collide with the neighboring Andromeda galaxy, a slow process unfolding over billions of years. Stars will pass each other without collision due to vast distances between them. Yet gravitational forces will reshape the galaxies into a new form. The universe at galactic scale is both dynamic and immense. Clusters form patterns over hundreds of millions of light years. Superclusters stretch across billions of light years, linking galaxies in vast networks. Within these scales, human concepts of size and distance fail. Numbers become abstract, yet they define the structure of the cosmos. The Milky Way is a dense island of matter in a largely empty expanse. Yet even within this island, the majority of space is empty. Stars, clouds, and clusters occupy a tiny fraction of the volume, while vacuum dominates. Our perception is limited. Night skies give an impression of countless stars, yet each visible point is part of a complex galactic architecture. Beyond sight, gravity and motion govern the invisible majority. The Milky Way's structure guides motion at scales beyond human experience. Spiral arms rotate, stars orbit, and the central bulge pulses with gravitational energy. Black holes lurk unseen, massive yet small in size, influencing nearby stars. Dark matter forms an invisible halo, extending far beyond the visible disk, holding the galaxy together against the centrifugal forces of rotation. Clusters of galaxies reveal patterns beyond imagination. The local group contains the Milky Way, Andromeda, and dozens of smaller galaxies. Their mutual gravity defines orbits and interactions, while the space between remains vast and cold. Larger structures, superclusters, link these groups into webs, forming a cosmic network. Filaments stretch across hundreds of millions of light years, voids spanning even more. Gravity sculpts the universe, shaping patterns at every level, from stars to galaxies to superclusters. Human perception cannot intuit these scales. Numbers must guide understanding. Hundreds of billions of stars, millions of light years, trillions of solar masses. Even imagining such distances is nearly impossible, yet each value corresponds to real, measurable phenomena. The Milky Way is both immense and tiny. Immense in its number of stars and reach across space. Tiny compared to clusters, filaments, and superclusters that span millions of light years. It is a single node in a web of matter and energy, connected yet isolated in the vast universe. Observing from Earth, the night sky offers a hint of this grandeur, but true scale is only revealed through instruments and calculation. Galaxies, clusters, and filaments all move, interact, and evolve. Time at this scale stretches billions of years, yet the laws of physics remain constant. The stars, gas, and dust obey gravity, light moves across distances at finite speed, and matter arranges itself into patterns, emerging and disappearing slowly across cosmic epochs. And as we consider the Milky Way, its size, structure, and motion, we begin to see that even these immense patterns are small compared to the universe itself. where billions of galaxies stretch across space, forming the largest structures ever known. The question grows. If the Milky Way is only one galaxy among billions, how vast is the universe, and how does human perception compare to its immensity? Beyond individual galaxies, the universe organizes into vast structures. Galaxies are rarely alone. They gather into clusters, each containing hundreds or thousands of galaxies. Gravity binds these clusters, holding them in relative proximity while the empty space between stretches for millions of light years. The clusters themselves are part of superclusters, immense aggregations spanning hundreds of millions of light years. The Milky Way belongs to the local group, a small cluster that includes Andromeda and dozens of smaller galaxies. The local group is part of the Virgo supercluster, a region containing thousands of galaxies. These superclusters are not uniform. Dense knots of galaxies sit at intersections, while enormous voids, regions nearly empty of matter, extend across space. Between clusters, filaments stretch like threads in a cosmic web. These filaments guide the formation of galaxies, connecting clusters, shaping the largest structures in the universe. The scale is difficult to imagine. Light takes millions of years to travel from one cluster to another. Distances that dwarf our previous concepts of size now dominate the cosmos. Even clusters appear tiny on maps of superclusters, and superclusters themselves are points in larger arrangements. Observations of these structures rely on light collected over immense periods. When we see a galaxy, we see it as it was millions of years ago. The light traveled across empty space through the cosmic web, revealing a past that no longer exists in exactly that form. The universe at this scale is both vast and dynamic. Galaxies move relative to one another. Collisions occur over billions of years, merging clusters or distorting shapes. Gravity dictates these motions, pulling matter into webs and knots, while empty space expands between them. Dark matter dominates the formation of these structures. Invisible and undetectable by direct observation, it exerts gravity, shaping the paths of galaxies and clusters. Without dark matter, filaments would not form, and the cosmic web would not exist as we see it. Though unseen, its effects are measurable, guiding the growth of structure on the largest scales. Galaxies trace its presence, moving along the invisible scaffolding that permeates space. Emptiness dominates. Even in clusters, most of the volume is empty, punctuated by galaxies and gas. Yet the gravitational influence of visible and invisible matter organizes motion, shaping the universe's structure over billions of years. Our eyes perceive only the light from stars and galaxies. Telescopes expand this vision, yet most matter remains hidden, either dark, distant, or faint. The difference between what exists and what we see is enormous. Visible light reveals only a fraction. Dark matter, dark energy, and faint, distant galaxies constitute the majority of the universe's content. Observing clusters shows motion, interaction, and evolution. Galaxies merge, orbit, or drift apart. Filaments guide new galaxy formation. Voids expand as gravity pulls matter toward dense regions. Time at this scale stretches over billions of years. Events that seem slow are transformative across cosmic epochs. Distances are so large that even light requires millions of years to traverse them. Measuring these scales uses units of millions of light years, a concept almost beyond human experience. Filaments stretch across space like threads connecting clusters, tracing a web of matter that dominates the observable universe. The cosmic web is intricate, a lattice formed by gravity acting over billions of years. Knots, filaments, and voids create the backbone of the universe, dictating where galaxies can form and how they move. Observations reveal that superclusters are not isolated. They interconnect, forming larger structures stretching across billions of light years. The emptiness between them is enormous, yet gravity slowly pulls galaxies together, shaping motion and evolution. Clusters themselves are dynamic. Galaxies orbit one another, sometimes colliding and merging. Gas clouds swirl, heated to millions of degrees, emitting X-rays that reveal mass invisible in optical light. Dark matter provides the scaffolding for these interactions, unseen yet essential. The visual universe is only part of reality. Telescopes detect some radiation, but much remains hidden, leaving space mostly unseen. Vast distances, millions of light years apart, mean we see objects as they were in the past. A cluster observed 100 million light years away shows galaxies frozen in time, their current state unknown to us. Motion is slow to human perception, yet continuous. Gravity guides stars, galaxies, and clusters, shaping paths over millions and billions of years. The scale of intergalactic space dwarfs human experience. The solar system is a tiny dot, the Milky Way a mere speck, the local group a faint cluster within a supercluster, itself a point in the larger cosmic web. And beyond even these structures, the universe expands further, stretching filaments and voids across unimaginable distances. Observing the cosmos this way highlights the difference between what we see and what exists. Light shows stars and galaxies, yet most of the universe is unseen. Dark matter dominates, voids stretch across millions of light years, and the vast majority of space is empty. The scales overwhelm intuition. Time, motion, and distance operate at levels beyond daily experience. Even imagining these structures is challenging, yet careful measurement, calculation, and observation reveal a universe organized into a complex network. This cosmic web sets the stage for the largest scales, where superclusters are themselves just components of a universe that continues to expand. And as we examine this intergalactic tapestry, we are forced to confront the limits of human perception. What appears empty may contain unseen mass. What seems stable is in motion. And the vastness of distances leaves us dwarfed in comprehension. Each galaxy, cluster, and filament exists within this structure, shaped by forces we cannot see, yet measurable through their influence. Light years define space, billions of years define time, and dark matter defines form. The universe is immense, far beyond human sight, and yet our understanding grows steadily, revealing patterns and connections that span unimaginable scales. If clusters and filaments form the scaffolding of the cosmos, how much larger is the universe itself, stretching beyond observation, beyond even the cosmic web that we can measure? And what does it mean to exist as a small, fleeting observer within such enormity? The universe begins in a state we cannot see directly, yet evidence remains in the oldest light, the cosmic microwave background. At roughly 380,000 years after the Big Bang, the universe became transparent. Before this, matter and radiation were coupled, a hot, dense plasma. Light could not travel freely. As the universe cooled, atoms formed, and photons moved across space without scattering. This moment left an imprint, a faint glow now observed as microwaves. The cosmic microwave background provides a map of early fluctuations. Tiny variations in temperature and density mark the seeds of all future structures. Galaxies, clusters, and filaments emerge from these minute differences, growing slowly under gravity's pull. The scale of the universe, then, was smaller than today, yet already vast beyond human comprehension. Early structures were simple, diffuse regions of gas. Over billions of years, these regions collapsed into the complex forms we see now: galaxies, spiral arms, and star clusters. Matter concentrated, forming stars, then planets. The contrast between these early clouds and modern galaxies is immense. A diffuse gas cloud, spanning thousands of light years, eventually forms billions of stars in a single galaxy. Time stretches across billions of years. Light from early galaxies travels for tens of billions of years before reaching us. When we observe distant galaxies, we see them as they were long ago. The further away we look, the younger the universe appears. This provides a natural clock, linking distance with age. The universe expands continuously. Galaxies move apart as space stretches. Distances that were once smaller grow over time, creating an observable horizon. Light from beyond this horizon has not yet reached us. The observable universe is defined by this limit. The maximum distance light has traveled since the beginning. Beyond it lies more space, unseen, but likely, containing similar structures, expanding just as ours does. The expansion affects scale. Objects once close together now sit millions or billions of light years apart. Motion is not due to the objects themselves moving through space, but space itself stretching. Galaxies appear to recede, their light redshifted, shifted to longer wavelengths by expansion. Observing these shifts allows measurement of speed and distance, revealing the universe's growth over time. Time and scale intersect here. Light from the early universe shows both distance and age. When we look far away, we see far back. A galaxy a billion light-years distant is seen as it was a billion years ago. This relationship ties human observation to cosmic history. The early universe was uniform in temperature, yet small fluctuations gave rise to the complex cosmos we see today. Density variations, amplified by gravity, guided formation of stars and galaxies. Over billions of years, these small differences grew into clusters, superclusters, and filaments. The cosmic microwave background is nearly uniform, yet tiny variations are crucial. They represent the blueprint for all structure. Without them, the universe would remain a smooth, featureless expanse. Observing this light reveals temperature differences of only a few millionths of a degree. Instruments detect this faint signal across the sky, mapping ancient density patterns. The scale of these variations is immense. Each tiny fluctuation corresponds to a region hundreds of thousands of light-years across in the early universe. These seeds expand, collapse, and merge, forming galaxies that contain billions of stars. The expansion also affects observation. The universe is roughly 13,800,000,000 years old. Light from the most distant objects has traveled nearly the age of the universe. The observable limit is set by this time and the speed of light. Beyond this horizon, light has not reached us. Space continues beyond, unseen but implied. Time and distance are linked. Looking further away means looking further back. Early structures were simple, yet the seeds of complexity were present. Gravity amplified tiny differences, building stars, galaxies, and clusters. Matter organized over billions of years, shaping the universe into its present form. Expansion stretches space, moving distant galaxies apart, while cosmic structures grow slowly under gravity. Observing the cosmic microwave background provides a snapshot of this early time. It is a map of density variations that gave rise to all structures we see. Filaments, voids, clusters, and galaxies all emerge from these tiny irregularities. The observable universe is finite, limited by light's travel time, yet likely much larger. Structures beyond our view may mirror those we see, expanding with the same cosmic rhythm. Early universe physics governs present structures. Temperature, density, and expansion set the stage for star and galaxy formation. Time and scale are inseparable. Billions of years transform diffuse gas into complex systems. Light carries this history across space, allowing observation and measurement. Instruments detect not only photons from distant stars, but also subtle signals from the cosmic microwave background. These measurements reveal fluctuations, composition, and the rate of expansion. Over billions of years, structures evolve. Galaxies collide, stars die, new stars form. Cosmic expansion separates clusters, stretches voids, and defines distances at the largest scales. The universe is vast, expanding, and evolving. Early structures were simple and uniform. Modern galaxies are complex and varied. Time and scale intersect, revealing a universe that grows, stretches, and organizes itself according to physical laws. The faint glow of the cosmic microwave background reminds us of the universe's youth, a time when atoms formed and light traveled freely. Observing this ancient light connects human perception to events billions of years ago. It demonstrates how vast distances correspond to immense spans of time. Scale is both spatial and temporal. The early universe was smaller, yet structures already spanned thousands of light years. Expansion stretches space, making these structures grow farther apart. Observing distant galaxies reveals them as they were, tracing the history of formation, collapse, and growth. Dark matter guides this evolution. Its gravity pulls matter together, shaping galaxies and clusters. Without dark matter, cosmic structure would be different. The universe we see is a product of both visible and invisible mass, interacting over billions of years across distances far beyond human experience. And as we trace the path from the cosmic microwave background to modern galaxies, we realize that the universe is vast, expanding, and ancient, and that every point in space carries a story billions of years in the making. If this is the scale of the observable universe, how much larger, older, and stranger is the universe beyond what we can see? The observable universe stretches across an immense distance, more than 46 billion light-years in every direction from Earth. Its radius defines the limit of what light has traveled since the beginning of time. Space itself expands as the universe grows, carrying galaxies away from one another. Even light, traveling at 300,000 kilometers per second, takes billions of years to cross the vast emptiness between the farthest galaxies. The volume of the observable universe is enormous. It contains everything whose light has reached Earth: stars, galaxies, clusters, gas clouds, and dark matter. It is a sphere defined not by the edge of space, but by the reach of light. Human perception fails here. Numbers lose meaning when distances are measured in billions of light years. A single light year is already 9 trillion kilometers. Multiply that by 46 billion, and the scale becomes almost impossible to imagine. Even the entire Milky Way, with its hundreds of billions of stars, is but a tiny speck within this vast sphere. Cosmic expansion shapes this scale. Galaxies move apart not because they travel through space, but because space itself stretches. Light from distant galaxies travels through expanding space, so the distance to these objects now is greater than the distance their light traveled. Galaxies that emitted light billions of years ago are much farther away today. This stretching means that the observable universe is larger than simple calculations of light travel might suggest. As we attempt to grasp these distances, human intuition fails. We cannot visualize billions of light years, trillions of kilometers, or the passage of billions of years. The universe operates on scales outside daily experience. Even imagining all the galaxies, stars, and planets within this immense volume challenges the mind. Numbers alone are insufficient. We rely on models, maps, and simulations to comprehend size. The observable universe is a bubble of light and matter, a sphere encompassing all that we can measure. Beyond this bubble, the universe continues. Light has not yet reached us from those regions, but matter exists, likely forming structures similar to those we see. Cosmic expansion means that parts of the universe recede faster than light can travel toward us. These regions remain forever beyond observation, yet they contribute to the total size of the universe. Gravity and motion within the observable universe create structure. Galaxies cluster, clusters form superclusters, and voids dominate the spaces in between. Expansion stretches everything apart, yet gravity pulls matter together into patterns. The interplay of expansion and gravity defines scale across billions of light years. The observable radius is a natural boundary for perception. It is not a wall, but a horizon set by time and light. Within this horizon, we see history, the universe as it was when light began its journey. Farther distances reveal earlier moments, younger galaxies, and simpler structures. The vastness challenges comprehension. Even imagining traveling from one side of the observable universe to the other exceeds human experience. Time required would be billions of years. Distances are so large that conventional measures like kilometers or miles fail to convey meaning. Light years, billions of years, and expansion rates are necessary units. Cosmic expansion also stretches wavelengths of light. Light from distant galaxies shifts toward the red, allowing astronomers to calculate how fast galaxies recede and how far they are. Observing these shifts reveals scale and the dynamic nature of space. Scale is not only spatial, but also temporal. Looking outward is looking back in time. The radius of the observable universe corresponds to the universe's age and the speed of light. Light from the farthest objects left when the universe was only a few 100 million years old. The volume defined by this light is enormous, yet it is only a portion of the entire universe. The true size likely extends far beyond what is visible. Expansion and gravity combine to form patterns on all scales. Filaments, clusters, and voids dominate the cosmic web. The observable universe is one sphere in this vast expanse. Human intuition struggles to comprehend it. Our senses evolved to measure meters, kilometers, and planetary distances. They fail when confronted with billions of light years, trillions of stars, and billions of galaxies. Yet measurement is possible. Observations, simulations, and physics provide understanding where intuition cannot. The sphere of the observable universe contains billions of galaxies, each with billions of stars and countless planets. Distances stretch across billions of light years, yet the universe continues beyond. Expansion carries galaxies away, stretching light and space together. Time and distance intertwine. Looking outward is looking into the past. Human understanding relies on mathematics and physics, yet even these tools struggle to convey the immensity of scale. Observing the observable universe is observing billions of years of history, billions of light years of distance, all compressed into the light reaching Earth. The universe is vast beyond comprehension, its radius defining the limits of sight, measurement, and human intuition. Yet even this immense sphere is only part of a larger reality that stretches farther, older, and more complex than observation can reveal. If the observable universe is this large, what lies beyond, and how much more immense is the total universe we cannot see? Within the observable universe, the number of galaxies is staggering. Estimates suggest more than 2 trillion galaxies fill this immense volume. Each galaxy contains billions of stars. The Milky Way alone holds over 200 billion, yet it is only one of countless others. Some galaxies are massive, spiraling across hundreds of thousands of light years, with hundreds of billions of stars. Others are small, faint dwarf galaxies, irregular in shape and far less luminous. Stars vary in size, mass, and brightness. Some burn steadily for billions of years, like our Sun. Others are massive, short-lived, exploding in brilliant supernovae that scatter elements across space. Around stars, planets orbit. Planets number in the trillions across the observable universe, ranging from rocky worlds like Earth to gas giants larger than Jupiter. Distances between these objects are immense. Light from nearby stars takes years to reach us. From distant galaxies, billions of years. The scale defies human intuition. Even imagining the distance from Earth to a single star, then multiplying by trillions, challenges comprehension. Cosmic expansion stretches these distances further. Galaxies once closer together are now receding, carried apart by space itself. Light traveling from the farthest objects has journeyed across space that has stretched significantly, making their current distance far greater than the distance light traveled. The structure of the observable universe is not uniform. Galaxies cluster together under gravity. Clusters form superclusters, vast groupings that stretch across hundreds of millions of light years. Between clusters lie voids, regions of space almost empty of galaxies. Filaments connect clusters, forming a cosmic web. Galaxies trace these filaments, moving slowly along the gravitational scaffolding created by dark matter. The largest filaments span hundreds of millions of light years, while voids may stretch across even larger regions. Gravity continues to shape this arrangement. Galaxies orbit clusters, merge with neighbors, or drift apart slowly. Clusters themselves are in motion, pulled toward dense regions or orbiting massive structures. Stars within galaxies move according to the galaxy's gravity, while planets orbit their stars. All motion occurs on scales far beyond human experience. Despite the immense emptiness, matter organizes itself into recognizable patterns. Filaments appear as thin threads connecting clusters, and dense regions form knots where clusters congregate. Observing these structures requires instruments. Light from distant galaxies arrives faint and stretched, yet it reveals positions, movement, and composition. Redshift shows motion, brightness shows mass, and spectral analysis reveals elements. The observable universe contains galaxies in all stages of development. Some appear as small, irregular forms, seen as they were billions of years ago. Others are fully formed spirals or ellipticals, mature galaxies glowing steadily. The range of evolution is immense. Stars form and die, Galaxies collide, and clusters grow over cosmic time. Each galaxy hosts planets, possibly billions, with unknown possibilities for moons, atmospheres, and even life. The scale of these contents is beyond human perception. Numbers alone are abstract. 2 trillion galaxies, billions of stars in each, trillions of planets orbiting those stars. Distances between galaxies stretch billions of light years. Cosmic expansion separates these structures, yet gravity binds them into the patterns of clusters, superclusters, and filaments. Light from each galaxy takes time to reach us. Observing a galaxy 10 billion light-years away is seeing it as it was 10 billion years ago, when the universe was young. Its stars may have evolved, its structure changed, but the light preserves a record of its past. Mapping these objects shows the cosmic web. Filaments connect clusters, outlining vast patterns. Voids appear as dark gaps between these luminous structures. Superclusters form dense knots, each containing thousands of galaxies. Gravity guides motion along these threads, shaping structure over billions of years. Even within filaments, galaxies interact. Collisions occur, stars are born and die, and matter flows through intergalactic space. The observable universe is thus both full and empty. Billions of galaxies provide structure, yet most of space is a void, dominated by dark matter and energy. Human intuition fails to grasp the vastness, but observation allows measurement. Instruments detect light across the electromagnetic spectrum, from visible to infrared, radio, and high-energy radiation. Data reveal the number, type, and motion of galaxies, stars, and planets. Patterns emerge, showing clustering, filaments, and voids. These measurements confirm theoretical models of cosmic structure and expansion. Even the most distant galaxies provide information. Deep-field images capture faint light from early objects, revealing small, forming galaxies when the universe was only a few 100 million years old. Over time, these galaxies grow, merge, and evolve into the massive structures we see today. The observable universe is immense, both in size and contents. Galaxies, stars, and planets fill the space we can see, forming clusters, filaments, and superclusters. Yet even this immense volume is only a fraction of the total universe. Beyond the observable horizon, more galaxies exist, more stars, more planets, forming structures likely similar to what we detect. Distances, numbers, and motion operate on scales beyond human experience. Time stretches across billions of years, distances across billions of light years, and yet observation allows understanding. The content of the observable universe reveals patterns, evolution, and the vastness of space, while highlighting the limits of perception. It is both an immense arena and a record of history, a testament to the organization and scale of the cosmos. As we trace galaxies across billions of light years, measure clusters and filaments, and count stars and planets, we confront the immensity of existence and the tiny, fleeting place of humanity within it. Observing the observable universe requires instruments that extend our senses far beyond human limits. Telescopes on Earth and in space collect light across the electromagnetic spectrum. Optical telescopes capture visible light, revealing stars and galaxies. Infrared instruments penetrate clouds of dust, showing hidden structures and forming stars. Radio telescopes detect cold gas and distant pulsars. X-ray and gamma-ray observatories reveal energetic events invisible to human eyes. Each instrument provides a different perspective, combining to form a complete picture of the universe's contents. Light is the messenger. It travels across space, carrying information about objects billions of light years away. By measuring this light, astronomers determine distance, motion, and composition. One crucial measurement is redshift. As the universe expands, light stretches, shifting toward longer wavelengths. The greater the redshift, the faster the object recedes and the farther away it is. Redshift maps the expansion of space and allows a calculation of cosmic distances. Light travel time adds another layer of understanding. Observing a galaxy 10 billion light-years away shows it as it was 10 billion years ago. We see its past, not its present. The observable universe is a record of history, frozen in photons traveling across time and space. Instruments also detect faint signals from the cosmic microwave background, the oldest light in the universe. This faint glow reveals density fluctuations from the early universe, guiding the formation of galaxies and clusters. Observations require precision. Distances are calculated from redshift, brightness, and angular size. Velocities are measured from spectral lines. Mass is inferred from gravitational effects on neighboring objects. Patterns emerge, showing filaments, clusters, voids, and superclusters. Gravity and dark matter shape these structures over billions of years. The cosmic horizon defines the limit of observation. Light from beyond this horizon has not reached us. This boundary is not fixed. It depends on the age of the universe and the speed of light. Beyond it, matter exists, yet it remains unseen. Human perception fails entirely at these scales. Our senses evolved for meters, kilometers, and daily life. They cannot grasp billions of light years or billions of years of cosmic time. Instruments replace intuition, turning faint photons into measurable quantities. Yet, even with technology, much remains hidden. Dark matter cannot be seen directly, yet its gravitational effects reveal its presence. Dark energy dominates the expansion of the universe, shaping distances and motion. Observations detect its influence, though the substance itself remains mysterious. Despite these limits, measurement allows understanding. Distances, mass, composition, and motion of objects across billions of light-years can be quantified. Maps of the cosmic web reveal filaments and voids. Deep-field images show galaxies forming in the early universe. Surveys catalogue millions of objects, tracing structure and evolution. Instruments make the invisible visible. They detect light that has travelled across space for billions of years, uncovering the past and revealing patterns too vast for human senses alone. Data from multiple wavelengths combine to show gas clouds, star formation, galaxy collisions, and the influence of dark matter. Each observation extends comprehension, yet also emphasizes limits. The universe is far larger than the observable portion. Beyond the horizon, more galaxies, more stars, more planets exist, but light has not yet reached Earth. Human perception is bounded by both the speed of light and the tools we create. Observing distant objects is a balance between what is detectable and what exists. Instruments measure what light reveals, but cannot show all matter or all structure. Even so, measurements reveal order in the apparent chaos. Filaments connect clusters, voids define emptiness, and superclusters form patterns stretching across billions of light-years. Each observation confirms theoretical models of cosmology, expansion, and structure formation. The universe is measured, yet it is immense beyond comprehension. Instruments provide knowledge where intuition fails. Observations of redshift, light travel time, and cosmic structure allow a view of the universe across space and time. The cosmic horizon defines limits, yet within these boundaries, billions of galaxies and stars are mapped, counted, and studied. Dark matter shapes motion, dark energy drives expansion, and visible matter traces patterns. Human senses are inadequate alone, but instruments reveal complexity and scale. Even so, the total universe extends beyond the observable limit, unreachable by light or measurement. Observing the observable universe illustrates both achievement and limitation. Understanding structures, motion, and distances across billions of light years, yet confronting regions forever hidden. The combination of precise instruments, careful measurement, and theoretical understanding allows humans to grasp the scale of space and time. From redshift to deep field imaging, from mapping clusters to tracing filaments, the observable universe becomes a comprehensible, measurable domain. It is immense, structured, and dynamic, yet still only a portion of the total cosmos. Human intuition cannot grasp billions of light years, billions of galaxies, or the motion of structures over cosmic time. Measurement allows perception, but awareness of limits remains. Beyond the horizon lies more, perhaps infinite, yet unseen. The observable universe is vast, measured, and mapped, but it is only part of a greater, expanding reality that continues beyond sight, beyond light, beyond what humans can directly perceive. After tracing the universe from the smallest scales to the farthest reaches of observation, a sense of perspective settles. Human perception is limited, shaped by daily life on Earth. We measure distances in meters and kilometers, time in seconds and years, and yet the universe stretches across billions of light years and billions of years of time. The gap between experience and reality is immense. Our senses perceive only a tiny fraction of what exists, and our intuition struggles to grasp the immensity of space or the brevity of our lives in cosmic terms. Earth, a planet of oceans and continents, mountains and valleys, appears large in our perception, yet it is just one small sphere orbiting a medium-sized star, itself one among hundreds of billions in the Milky Way galaxy. The Milky Way is part of a local group of galaxies, which forms part of a supercluster which connects along filaments in the cosmic web. Each scale grows larger, revealing new layers of complexity, yet also reminding us of human smallness. Humanity occupies only a brief moment in time, a fraction of a second in the 13 billion years of cosmic history. Civilizations rise and fall, stars are born and die, galaxies merge, and cosmic structures evolve over periods far beyond our comprehension. The sheer scale makes events on Earth seem almost impermanent, yet within this small space, life has arisen, adapted, and flourished. Life itself is a product of cosmic history. Cells formed, evolved, and multiplied, creating diversity unimaginable in numbers and complexity. Planets provide stable conditions, star cycles provide elements, and the laws of physics govern matter from the smallest quarks to the largest galaxy clusters. Understanding the scale of the universe invites reflection on significance. Humanity is small in size, short in time, and limited in perception. Yet within this small sphere, consciousness, curiosity, and creativity have emerged. Humans observe, measure, and understand. Instruments extend our senses, revealing light from the farthest galaxies, mapping the cosmic web, detecting dark matter, and tracing cosmic history. Knowledge allows comprehension where intuition fails. Awareness of scale inspires humility. From the Planck length to the cosmic horizon, distances and sizes dwarf human experience. Each galaxy contains billions of stars. Each star may host multiple planets. The observable universe is a fraction of a larger whole, perhaps infinite, yet the patterns we detect show order and structure. Contemplating this immensity leads to philosophical reflection. Life is tiny, yet it is aware. Earth is minuscule, yet it harbors complexity and richness. Stars and galaxies are vast, yet matter arranges into recognizable patterns under gravity. The infinite contrasts with the tiny, yet both coexist in a single universe governed by physical laws. Time and scale intersect in our observation. We see distant galaxies as they were billions of years ago, capturing a record of cosmic evolution. Space expands, structures move and grow, and yet light preserves the story, allowing understanding despite immense distances. Human perception measures only a fraction of reality, but reflection, mathematics, and observation extend comprehension. Awareness of scale influences thought, philosophy, and perspective. Our lives are brief, our bodies small, yet our minds can trace structures billions of light years across, contemplate billions of years of history, and imagine a universe far larger than our observation allows. Awe arises from contrast. The enormous distances, the countless stars, the intricate patterns of galaxies, and the simplicity of human daily experience. Wonder emerges from understanding that life exists at all, given the immensity of space, the extremes of time, and the delicacy required for conditions suitable for consciousness. Calm reflection follows. Observing the universe is not only about size, but about understanding place. Humans are small, but capable of insight. Earth is fragile, yet stable enough to support life for billions of years. Galaxies and clusters evolve on their own timescales, indifferent to individual existence, yet humans can detect, measure, and describe them. Perspective grows. From quarks to cells, from planets to galaxies, from clusters to superclusters, each layer of scale reveals beauty and complexity. Understanding comes slowly, patiently, through observation, measurement, and reflection. The universe operates on physical principles, indifferent to human meaning, yet humans can find purpose through knowledge, awareness, and appreciation of scale. Contemplating the vastness calms the mind, placing daily concerns in context. Worries shrink when measured against billions of light years and billions of years. The rhythm of cosmic evolution contrasts with human temporality, yet the same physical laws govern both. Awareness of scale nurtures humility and wonder, emphasizing both smallness and connection. Humanity exists within the universe, composed of the same elements as stars, shaped by the same physical laws. Consciousness allows observation of the universe, making awareness itself a product of cosmic evolution. The infinite and the tiny intersect in the act of seeing, measuring, and understanding. Reflection deepens. The observable universe contains billions of galaxies, trillions of stars, countless planets, yet humans can map, count, and study them. Instruments translate faint light into information, revealing structure, motion, and composition. Observation shows both immensity and pattern. Cosmic structures, from filaments to voids, reveal order. Galaxies evolve, clusters form, and matter organizes over billions of years. Human understanding extends into this vastness, bridging perception and reality. Calm arises from comprehension. The universe is immense, structured, expanding, and ancient. Human lives are short, yet observation allows participation in cosmic history. Knowledge of scale fosters both humility and connection. We are part of a greater system, observing from within, yet able to comprehend far beyond direct perception. Contemplation of the universe's size, time, and structure creates awe. Recognition of human smallness coexists with appreciation for insight, understanding, and the ability to perceive. The infinite stretches beyond view. The tiny exists in our hands. Both can be understood through patient observation and reflection. The universe is immense, yet comprehensible. Humanity is brief, yet aware. Awareness allows reflection, understanding, and a sense of wonder. Looking outward is looking into the past and across unimaginable distances. Observing and measuring, humans connect with structures billions of light-years across, witnessing formation, evolution, and the patterns of matter itself. From quarks to galaxies, from life to cosmic filaments, scale informs perspective. Reflection invites calm. Awareness of scale fosters humility. Understanding fosters awe. The infinite and the tiny coexist. Consciousness allows perception. Observation allows comprehension. Humanity sees, measures, and contemplates. The universe is vast, yet patterns emerge. Life is brief, yet aware. Space is immense, yet ordered. Time is long, yet recordable. Observation, reflection, and understanding create a sense of connection and calm. In this awareness, wonder grows, insight emerges. Human perception, limited though it is, bridges the gap between the minuscule and the infinite. Earth, life, stars, galaxies, clusters, and cosmic filaments all exist in a single universe, bound by the same laws, observed and understood, giving rise to reflection, awe, and a quiet sense of place. And as we pause in contemplation, the mind can rest, recognizing the smallness of self, the grandeur of the universe, and the ability of awareness to perceive, measure, and understand it all. In this calm realization, human life finds perspective, fleeting yet conscious, small yet capable of understanding, ephemeral yet connected to a cosmos that is vast, ancient, and endlessly complex.